Hello, I'm Rhonda Stevenson.
Status check to proceed with terminal count. First stage system. Propulsion.
Go.
Hydraulics.
Go.
Locks.
Go.
LH2.
Go.
Vehicle system engineer.
Go.
Anomaly chief. Go. Range coordinator.
Clear to proceed.
Launch director. You have permission to launch.
We have liftoff of the United Launch Alliance.
Liftoff of the United Launch Alliance Delta IV rocket.
And we have good indication of separation.
Hello, I'm Rhonda Stevenson, and welcome to Space Matters. Today, we'll be visiting with part of the team from Orbital Assembly Corporation. Unfortunately, not everyone was able to join us today, so we will be having a follow-up episode that will include those team members that weren't able to participate in today's discussion. I hope you enjoy this episode of Space Matters.
Orbital Assembly Corporation today had a very successful demonstration of our station truss assembly robot. We moved 6 tons of steel and built a football field length of truss in a record time. And this is going to allow us to build large structures in space. And we're very proud and excited of what our team accomplished today.
We'll be able to build many things, but one of the kinds of things we can build is space stations for tourism, for industry, and for research into a variety of things, such as the effects of the space environment on humans, partial G, all kinds of things that affect people when they're in space. We'll be able now to do that research and find out what do we have to do to make people thrive in space. Not just survive, but thrive.
I'm really excited about what we've demonstrated with the D-Star, what this automated assembly technology can do. It's like if you're camping and you get out to the wilderness and you're setting up a tent and you've got this work you need to do as a human to put up this living space for you. And what we've demonstrated with this is this underpinning of a livable space. It's like bringing a pop-up tent with you to the campsite, and you press a button, boom, you've got your pop-up tent just ready to go, and your living space is there waiting for you. And that's what just really gets me excited about this, is that we're enabling this automated assembly of new territory and space that just gets you started and ready to go in bringing humanity out, above the surface of the planet.
We're here. I'm ready. Let's go. Let's go to space.
Well, our goal is to launch the P-STAR mission in 2023 and to build the gravity ring through that. From there, we're developing out the initial elements of Voyager space station, and our goal still is to spin up Voyager in 2027. We believe that the capabilities that we're iterating, the advanced manufacturing technologies that we're using, and the experience of this team can do that. And that's really exciting because that not only opens up Voyager Station, but that also opens up client contracts for space infrastructure like solar platforms, computing platforms, propellant depots, or of course more Voyager stations.
The way that humanity is advancing right now, we have to do these things in order to basically survive in the future. Because there's various calculations that you can do and figure out if we keep evolving as a population or keep having population expansion, the amount of energy that we use over time compounds, and then we have to we end up getting to a stage in 400 years where basically the whole Earth would have to be covered in solar panels, which is not possible. So we have to explore new ways and methodologies and how to live off Earth and to keep humanity surviving, because if we don't, we're going to run out of resources and things like that we have on Earth to be able to leverage the things that we've learned here and the people that are here and then start applying them off Earth. It's about the learnings and the understanding of things that we will enable in space. So once we start living in space, we learn a lot more about what's available and what resources are available, and then what we can or cannot use on Earth to keep Earth sustainable. I think that's the most important part. We simply don't know what we can use, and we can speculate, sure, but until we're actually physically doing it, just like we did it today, we have to make a hardware demonstration of the things that we want to do so people understand. And then the same application will happen when we use this technology and we create the station and then we live on it, and then we start to learn a whole bunch of things that we didn't understand before. And people understand, and it's a new advancement in everyday lives. And then can we apply some of those learnings back to Earth? I'm sure there'll be some applications, for sure.
And we are going to space.
What's the time?
Time flies in space.
What? Oh, okay. Wait. What was it? 20?
25, 12, but let's say 24, 24.
Oh my god. 24. Oh my god.
All right, cool.
Yeah. Oh my god. 24 minutes. That's 24 That's amazing. Minutes. So, if you guys want to get in the line? You guys want to get in the line as before? Yeah. Amazing. Good job. So, Well done. You guys get in the line, just like the bank. Photo op. Once again. Video.
So, guys, just a little bit of quiet. I'm sure some other people had some questions, right? Or I was the only one. So maybe Tim, just explain to us like that whole process. Like, how's that going to work in space? Like, obviously, what happens when you're on around? Like, just give us a bit of the overview of what they just saw.
Yeah, absolutely. So as I was saying, inside there's one little piece that's not automated, and that's the bolt driving. So we've designed a mechanism to take that part over, and our next rounds of funding will fund the development and the construction of those bolt driver boxes. So if you notice, the slowest part was Eric. It's true. When we can replace him with a machine, we're going to crush that 24-minute time. Okay. And in orbit, we can build straight trusses on orbit, and there's lots of applications for that. With our P-STAR mission in 2023, we're going to build a circular truss. So it's going to come all the way around and plug back into the backside of P-STAR. P-STAR will detach, and then we're going to spin up that truss with payloads on it and then generate artificial gravity.
Wow, let's make some noise for that. Well, while we've got the whole team here, I'm sure there might be a couple of questions, obviously, because not everybody will be able to hear in one moment. Does anyone have any questions for the team?
So what are you the proudest of?
Gravity, hardest part.
Two answers to that. The hardest part was not building the truss. It was getting these things to keep gravity from clobbering us. When it came out, it wanted to go down. These things keep it from falling down. That turned out, because of the concrete sloping that way and sloping this way and being curved and so on, was actually more of a challenge than getting our machine to work. The proudest thing is showing that this team has come up with a method that can build big things in space.
Wow.
How does it feel for so many handsome guys work for a beautiful woman?
It's great.
I love working next to this handsome face.
Calm down, Jace.
I think there's another question over here.
Yeah. Do we have any other questions? Yeah. What's your name?
I noticed the whole system isn't particularly rigid. Will it be hard to match up the two ends when it gets to the circular form?
Yeah, so one of the things so the question was, he noticed that the system wasn't entirely rigid and it will be hard for that to match up.
Right.
So it's not entirely rigid because of budget cuts. So most of the D-STAR, the initial funding and fabrication was funded by the founders. And so we were operating on a very limited budget in order to get the demonstration done. If you notice, there's these cross frames are every other segment. And so those are the weak points where we didn't have those cross frames. So when we go to P-STAR and on orbit and we're building Voyager Station, we'll have all of those intermediate frames in place, and then that'll increase the rigidity. Did you want to add anything to that, Tom?
Yeah, as far as putting it out of the what we call the P-STAR in orbit, when that comes around, you can't be guaranteed it's going to be perfectly aligned to come in. So we're building into the joints a little bit of flexibility. So when it comes around to the end here, we can guide it in. There's enough flexibility to guide it in and mate the front end with the rear end and have a complete circle.
So what kind of fairing, what are we looking at to get this in orbit? You know, is this about the size of the unit, the orbit? Is it going to be a smaller unit? So, fairing size and everything. I assume your size is
Yeah, no, that's the first orbital system is going to be quite a bit smaller than this. This one, it's 2 meters, about 6'6", 6'7", across and vertical on the inside. We're going to be something like half a meter, or on the order of 20 inches on the inside. So it'll be much smaller. We can fit the whole thing into existing fairings.
So something like a Falcon 9 or even something on that size.
Yeah. So Tom brought up a good point there. So D-STAR here is 2 meters by 2 meters. You can walk through it. The gravity ring will be 1/4 this size, half meter by half meter. Voyager Station will be almost twice this size, and we have a tape outline on the pavement behind you of the center of a Voyager Station module, if you want to check it out. That's where we're headed. And to get the truss, the full-size truss for Voyager Station, we'll need heavy lift capabilities.
How will you take it out of SpaceX rocket? Because I understand you are choosing SpaceX to take it into space. And how will it look like to put it out there?
But we're evaluating several different launch companies. We want to make sure that it fits comfortably in a fairing. We haven't picked who our launch company is yet, but that's up for discussion.
And will you use astronauts in some part of the process? Because I know your goal is not to have humans assemble it in space, but do you plan to have astronauts present as a part of your mission?
Not in our first mission, no.
What other questions, guys?
And a follow-up to her question, how do I sign up to become one of those outfitters?
You're here, you're on the books.
I'll work for free.
Signed up. Yeah.
All right.
Sweat equity right there.
Hello, I'm Rhonda Stevenson with Space Matters, and today I am so excited to share with you the team from Orbital Assembly Corporation. So without any further ado, I'd like for each of these fine people to introduce themselves. Unfortunately, we are down 3 people in our team, and we will be having a follow-up episode so they can be introduced. So I'd like to start with Tim Alatorre. Tim, take it away. What's your role, and tell us about Orbital Assembly and where we're going.
Yeah, thanks, Rhonda. I appreciate that. My name's Tim Alatorre. I'm the chair of the board and the chief operating officer and VP of habitation design. And really excited to be here on the show. Orbital Assembly Corporation. We recently demonstrated our D-Star hardware, and we're the team that's going to be building Voyager Space Station, the first artificial gravity space station. We're going to have a space hotel, which has made it all across the news. We've been featured in a lot of different publications, and excited to talk to you today. And I'll let you go around the room and introduce the rest of the team.
All right, and then the next person we want to hear from is Dr. Tom Spilker.
Thank you, Rhonda. I'm Tom Spilker. I spent 20 years working at the Jet Propulsion Laboratory, a good part of that as a spaceflight mission architect. With OAC, I'm a founder and a board member and the vice president of engineering and vice president of space systems architecture design. I've had a lot of experience working with interplanetary spacecraft and a little bit of experience with near-Earth spacecraft, and I'm just really happy to be able to apply what I know about operating in space to building Voyager Space Station and all of the steps leading up to it.
Great, and then we'd like to hear from Dr. Jeff Greenblatt.
Hey everybody, I'm Jeff. I am the Chief Visionary Officer and Chief Scientist at Orbital Assembly Corporation. And my background is I'm actually trained as a chemist, and I've spent about 20 years working on environmental and energy systems topics, mostly related to climate change mitigation. But in the mid-teens, I got interested once again in space technology and started thinking about the ways that I could apply my training as a systems thinker to space activities. So at OAC, I'm also a co-founder, and I am leading the Gravity Ring project, which you'll be hearing more about soon.
And finally, last but not least, Tim Clements. Tell us about you.
Thanks, Rhonda. Thanks for having us on the show. So I'm Tim Clements, OSC Strategic Advisor for fabrication, assembly, bulk procurement, manufacturing, and engaging industry across the globe. How we can engage various technologies that have already been developed and apply them to our specific application. And I'm just really excited to be here, and this team is awesome.
This is an awesome team. This is an absolutely awesome team. One of the things that I was excited to ask you about, Tim Clements, is your advisory role with Orbital Assembly Corporation aligns really well with what you do and what your work experience is working with large structures. Can you expound on that a little bit?
Yeah, sure. So I have 20 plus years building basically anything. I'm one of those guys you come to when you need to build something that hasn't been done before. I've built manufacturing plants in 5 different countries around the world, from warships, luxury cruise vessels, civil infrastructure, oil and gas systems. Have quite a diverse background in many different disciplinaries, and the network that's associated with that's is helpful for Orbital Assembly to leverage.
Absolutely. And Tom, you've had some experience with the space program up to now. How do you bring that experience into what you do for Orbital Assembly?
Well, of course, JPL undertook some very challenging missions. This is one of the reasons that the Jet Propulsion Laboratory was created, to do kinds of missions that were not economically an objective, but were national priorities. And they involved exploring the outer solar system. I worked with the Voyager project. They involved exploring Saturn and the Saturn system more in depth with an orbiter. I worked with the Cassini project. I worked with the Genesis project that collected solar wind and brought it back to Earth. And each one of these involved designing spacecraft and proving the kind of design techniques and the design processes that wound up with very reliable spacecraft. So I got very familiar with those processes of designing and operating these very complex spacecraft. At JPL, I was also a member of what they called Team X, which was an advanced mission and project design team, and got to see a wide range of different disciplines involved with the upfront design of spaceflight missions and the spacecraft that are involved with those missions. So I got the breadth of experience in all of the different subsystems that a spacecraft has to have to operate as a fully independent spacecraft. And I'm bringing those to the table with OAC to make sure that the things that we build will actually work as intended.
Absolutely. Tim Alatorre, how does your background as an architect and your interest in habitats add to what you bring to our wonderful team?
Well, I think I bring 2 very different skill sets to our team. One, you didn't mention, is business and management. I've run companies and organizations, and as an architect, I've run jobs and projects incorporating teams and individuals and companies from a wide variety of different professions, backgrounds, and sectors. And so I bring that skill set of management and organization and business management to the team. And then as an architect, I've, like many of the people on this call here, I have decades of experience in my kind of chosen career. So as an architect, I've built and seen the construction of well over 600 different structures and projects in my career, ranging across a variety of different archetypes. And so what that's allowed me to do is I really understand how people interact with space, what people need to be able to feel comfortable, not only physically, but also mentally, emotionally in a space. And so as we're designing stations and habitats for people, my experience and understanding of human psychology and how we interact with the environment around us becomes really pivotal to designing stations and locations where people want to spend time and where they can thrive, really, and not just survive, not just camp, right? But really have a positive experience. So I bring a lot of different backgrounds to the team.
Wonderful. Jeff, can you walk us through what were the steps to get here? How did Orbital Assembly Corporation come to be?
Yeah, it's we've been talking a lot about this lately, and you know, several of us have known each other now for several years. I think we would all consider ourselves space nerds in the sense of being enthusiastic about space, but also in terms of having a lot of depth of knowledge of different areas of the field. And some of us started getting together and talking about some of the big problems that we saw in the space industry, and basically why people weren't already living and working in space by the millions, as many of us imagined might have happened, you know, after the Apollo moon landings. And you know, after I would say several of these meetings, we really honed in on a few key challenges that have kind of dogged the industry. up until recently. And one of them is, the ability to get stuff into orbit at low cost. Costs have remained stubbornly high for decades. And that really kind of hampers everything, because if you can't get anything up there, affordably, then you can't do very much. But then the other thing that we saw as a barrier was all the problems that people are having being in weightlessness for long periods of time, and identified that humans really need gravity in order to thrive for long periods of time, as well as making a lot of ordinary tasks a lot easier than if everything's floating around. And so the ability to provide artificial gravity in a cost-effective manner really was seen as paramount. And that, plus the ability to automate the construction of large scale structures, larger than what we've seen put up into orbit previously, is another key enabler. And we realized that we had some of these solutions in hand if we just put our heads together, formed a business plan, and frankly incorporated and started getting on with it. And so that's what eventually led to our formation of a company in late 2019.
Jeff skipped over a whole lot of meetings and conversations. It wasn't just like, hey, let's do this. There was a lot of thought and a lot of documentation and research that went into it before we started.
Well,
that was a good cliff
so
note
with
version.
that, with the meetings and a lot of the thought, what were your first steps? How did you get to where Orbital Assembly is today, with a successful demonstration event behind us? How'd we get there?
Well, Rhonda, there's a lot of what these meetings were talking about. These were architectural level discussions and architectural level calculations about, okay, if you want to provide a certain level of gravity, artificial gravity, how big do you have to be and how fast do you have to spin? What are the limits on how fast you can spin? And we were doing a lot of calculations about things like that, about how much mass does it take to provide a structure of that size? How much propellant would we be using each day for things like attitude control and drag makeup, to look and see if there were anything that looked like showstoppers. And as our calculations went ahead and we learned more and more about the situation, we weren't seeing these showstoppers, and we were realizing we can do this. Now is the time.
Yeah, I'll just add
coupled with that. Yeah, go ahead.
Oh, we're all excited to jump in. Go ahead, Tim. I'll fill in whatever you don't mention.
Well, I was talking about something that you were really involved in as well. Coupled with that, we were doing all the cost analysis and the market analysis, and saying, is there a market? Are there enough people who would be willing to go to space and would have the resources, the monetary resources, to afford a trip to space? And can we get those costs low enough to make it work? And so, that was all going on concurrently, and that's where Tom was saying, were there any showstoppers in there? No, the numbers we were seeing were very encouraging, to where we said, hey, we can just work. Let's do this.
Yeah, I was just going to add, I think part of what kind of helped to motivate us getting to where we are now is we did have this big vision of building a self-sufficient and economically viable space station in orbit that would be bigger than anything that has been built before, and that would really open the door to having space tourism become a more mainstream thing, with thousands of people visiting per year. But of course, that's a big vision, and it's still several years away from realization. And in terms of the next steps, we realized that we had to start by actually building something to prove our technical acumen and our ability to get a job done. And so that's what resulted in the construction of what's called the Demonstration Structural Truss Assembly Robot, or D-STAR, which we funded out of our own pocket and finally demonstrated for the first time to the world last month.
So with the D-STAR event, that was a fantastic proof of work. Tim, Clements, what was your take on how the demonstration went and how that gave us a proof of work to demonstrate that orbital assembly is actionable?
I think it's demonstrated a number of the things. One, that this team can design, build, test, and learn from various apparatus or robotics that we have designed in-house. It also just proves how much or highlighted the areas that we need to automate, which we already knew about, and help engage the rest of the audience on specific ideas and things like that I might have noticed. So that really helps contribute to the team. We go away and whiteboard and do a whole bunch of things to figure out what is our next steps and what are we going to learn from this and how we're going to apply it to our next iteration. So I think that's what it demonstrated the most. But the key point was what the team can do in a very short amount of time and a very strict budget. And I think that's quite pivotal to our next steps.
Yeah, if I could just add to that, I think, people watching the video of the demonstration and looking at what we published about it might not realize that the entirety of the program happened in the course of one calendar year and during COVID. So we were working under the constraints of all of the, the supply chain and manufacturing issues of a pandemic. On top of that, we were working with the funds that we had as the founders. And then, coupled with that, we built something of a serious size. We built a machine that built a truss that weighed 6 tons and stretched for almost 80 meters. It wasn't a small little laboratory experiment that we did in an office space. It was a serious piece of hardware. So, piggybacking on what Tim said, I'm really proud of our team. More than just the 5 of us here on this call. There were a lot of people involved with that, and to coordinate all that and get that all to come together really was validating for me of our team and our future capabilities.
All while remote as well, might I add, and some people that we hadn't had a face-to-face discussion with at all. So it's quite an interesting challenge, but it just goes to show that the things that we can do together as a team.
Yeah, where there's a will, there's a way, for sure. We're all animated by that goal.
Absolutely. One of the things that I wanted to draw a little bit of attention to is it's been said by a couple of different people here that that it was your personal investment. Now, did you have grants or did you have any other major investor come in and help you grassroot this objective from the beginning?
It's all out of our pocket initially, literally what we have in the bank to spare. And then we were able to go on and raise some money through crowdfunding in January. And at that point, we had so much interest already from the publicity, from some of the videos that we had published earlier, and from our own connections, that we were able to raise a significant seed funding of about $1 million, which helped to pay back what we had already invested personally. But yeah, prior to that, it had all been done basically on a shoestring.
Well, I'll just clarify what Jeff said there, that those funds haven't paid us back. Those investments from the founders are still sitting there as stock investments. But what that did allow us to do is to wrap up the D-Star program and do a demonstration, because we were enough to get the thing built. And then that, from our supporters, that allowed us to be able to demonstrate it, to put it together, get a facility, show it off. So that was a huge help.
And those funds are now launching us. Excuse me. Those funds are now launching us into design and architecture of the next steps that we're doing. So they're not sitting there unused.
So with the event and how things went, was it, and there will be the video, an abbreviated video of the event that will accompany this panel discussion. But how much of the proof of work demonstration was automated, and how does that impact or bring attention to some of the things that we still do need to invest in?
Yeah, well, virtually the whole thing was automated, with the exception of the bolting together of the different structural members, what were called the frames of this truss. And that is it's a complicated and key piece of the full automation, but everything else, the movement of these large pieces of steel sliding into precise alignment and then being extruded from one end of the machine, that was all programmed and really worked like a charm. I'll say one of the challenges in going from the system that we built to an actual space-worthy system is that everything has to work without any human hands. On the other hand, we won't be fighting against gravity the whole time, which I would say was probably our biggest technical challenge in getting the demonstration to work.
Mm-hmm. Definitely, gravity was the 100% the biggest challenge that we had throughout the whole process. If we didn't have that, we would have been pushing out good 200, 400 meters in 15 minutes or so.
And when they mentioned the bolts that needed to be driven and not being an automated system, it's not like each 20-foot section of the truss needed 100 bolts to be driven. It was 4 bolts. Each section needed 4 bolts to be driven, and then it went forward, and the next section got 4 bolts. So it was a fairly small piece of the entire structure that needed a non-automated process.
So this successful demonstration event utilized technology that exists today. So now Orbital Assembly has a proof of work, a proof of concept. Did you have to derive any new technology, or are we waiting for the discovery of an add-on that would be enabling for us to achieve the next steps?
No, we needed no new technologies, and in fact, the thing that we've identified as the non-automated part, the automatic bolt drivers, that's not actually a technology development. That's an engineering development, and that's different from a technology development. So with that engineering development, we can have a fully automated system.
Yeah, there's some very creative, I'm tooting our own horn here, but I think there's some very creative engineering that happened to make D-Star happen. How we put together those various truss segments to get the bolting down to 4 bolts, and the way we integrated and positioned all those bolts and the mechanisms that aligned everything, that was some very thought through engineering that is going to carry on into the subsequent projects. So there's a lot of IP developed with the D-Star program that's going to carry on all the way through, most likely to Voyager.
So what are the next steps? I mean, I know what the next steps are, but we need to explain to folks, what the sprint of the next 2 years for Orbital Assembly looks like, and what those objectives are. Who wants to start on that one?
I'd like to start, actually, because I'm heading this part of the program, and that is, so the next thing that we are working on, I mean, we're working on several things, but the main thrust of what we're doing next is we are building an orbital version of what was demonstrated on the ground. And we plan to finish, so we're well along in the engineering of that device already. We're calling it the Prototype Structural Truss Assembly Robot, or P-Star. And it's going to build this circular truss that we call the gravity ring. It's going to be a lot smaller than D-Star. D-Star is big. You can stand inside the square area of one of those truss segments, and the machine around it is even larger than that. We realized that building something of that size and launching into orbit, while definitely something that we will eventually need, and in fact will need something larger than that, did not make sense to build as the very next step, because everything is a lot heavier, more difficult to test and transport and to pay for. And so we're going with a smaller version that will be able to demonstrate the proof of principle of this, including all the automation steps. And it also allows us to be able to fabricate, test, and launch it within 2 years. So that is what we're now head down focused on. And everyone on the team is contributing to that in various ways. This will then allow us to demonstrate 3 things really. We'll be able to build and launch something in orbit. We'll be able to show the automated assembly of a large structure, larger than anything that's been built before in space, without a lot of human hands. And 3, we'll be building a circular truss, which can then detach from its parent spacecraft and spin to create artificial gravity for the first time at scale. So that is our next immediate goal.
So to recap this sprint to our next mission, which we anticipate launching in fall of 2023, The main objectives are basically to demonstrate that we can indeed build something in space, and that we can create gravity. It seems pretty simple. Is it simple?
It's not simple. There's a lot of moving parts, literally and figuratively, a lot of engineering challenges, although I think they're all easily surmountable, provided we have the time and resources. And we're making that happen, putting a lot of personal effort and sacrifice into the project as well. But it's eminently doable.
And
Tom, did
like
you
any
have
big project, I was
Sorry.
going to say, like any big project, you break it down into component parts and just start checking off the boxes. And so we have a lot of really organized, engineered system thinkers on our team. And, we have our marching orders. Jeff's heading that up, like he said, but we know that to be solved. And so we're just going through them one by one. And the team gets together, we talk it through, we find solutions and move on to the next one. So it's nothing right now that's going to stop us. We're on the way. Like Jeff said, head down all the way.
Yep.
As Tim indicated, that we take things and break them up into subtasks whenever possible, but any good architect and any good system engineer knows that if you're building a system as complex as a rotating spacecraft that's going to generate artificial gravity, you have to realize where all of these different pieces couple together. It's not like you're launching 6 or 8 or 10 things that all function separately in space. They all have to work together, and the architects and the system engineers need to know, where does that piece interface with this piece and this piece and this piece, and where are those kind of in the negligible side, and where are those critically important. So we do a lot of calculations involving those couplings between systems and making sure that one thing we design isn't stepping on another thing we design.
And I'll actually add something to that. We're a small organization. I mean, we certainly hope to grow, and we will have to grow by the end of this first project in order to be able to succeed. But we all talk together, and many of us are aware of several different of these sort of interrelated parts. And in a larger organization, sometimes those roles are siloed, and without recognizing the connectivity between things, important interactions can be missed. I think that we're in a good position to not miss those because of the degree of matrixing and cross-fertilization that we have right now. So I consider that a strength of a small team.
Absolutely. So Tim Clements, as a strategic advisor to Orbital Assembly, obviously this isn't cheap. This first mission is going to cost, and so I'm wondering what your thoughts are on what our funding outlets look like, and the progression of those. Do you have a comment on that?
So the question was funding streams to enable us to complete our missions.
Yep.
I don't know how much I should actually go into, because there's that many avenues that we can use to leverage to get to where we're going. That every day I wake up at 2 a.m. in the morning and I think of another idea. It's something that can contribute to this team moving forward. There is quite endless amount of possibilities that we can have with utilizing different technologies that's emerging now. Blockchain technology, industry engagement, and the people that we are engaging with right now are very interested in leveraging what we have. And I'm not sure if we should go into further detail right now what those things are, but it's very exciting. And the more people I talk to in behind closed doors, the more avenues we have. And I'm really excited just to move this forward at rocket pace.
Well, you teed that up perfectly, because the next thing that I wanted to outline is with regards to this next mission in 2 years, where we're building something and then we're creating gravity. That becomes an asset. And so what are your comments on what kind of value that brings to the rest of the space ecosystem? how does that become enabling for other space companies?
Essentially, we are creating real estate in space that others can leverage for research, development, other technologies, testing, and leveraging into other avenues of space that are yet to be explored, or in a habitat. So, again, the possibilities are limitless, unlimited right now. Every day we talk to someone, there's another use case that we can leverage. So again, really exciting to move those forward.
Does anyone want to take the comment on collaborative and future collaborative partnerships?
I can talk about that briefly, and then also just add a bit more to what Tim was saying there. That the point of having real estate in space, I think, is really key. Till now, there's been real estate in space. There's been places for companies and other entities to host payloads and do experiments, but they've all been government controlled. And Gravity Ring is going to be the first commercially operated platform with artificial gravity, no less, for hosting these payloads. And so that opens up a lot of opportunities, like Tim was alluding to. And one of our really near-term collaborative partnerships is with Rogue Space. They're a developer of robotic drones, satellites that perform various tasks on orbit to help service other craft. And we're working on some agreements and partnerships with them to have some collaborations and using their hardware to support our goal, our hardware. And then we're also looking at other entities and organizations as well. We talked a little bit last year in a couple of our broadcast interviews about possibility of partnering with space solar power companies, and there's still some ongoing discussions there. But like Tim was saying, there's a lot of opportunities. I'm not sure how much to get into, Rhonda, but I was just, for people watching, I said stay tuned as we get things more solidified and the ink dries, and we can start talking about it more.
Absolutely, and I think that it's important to touch on as we move forward with this next mission, and then the steps beyond. We're demonstrating that we're technologically applicable and that we have the scientific rigor to make these benchmarks happen. So what happens after we have this mission in 2 years, where we have successfully constructed something in space and produced gravity, and then that's an on-orbit asset? What comes after? What are the next steps after that? Or what are the simultaneous steps in tandem to that?
Yeah, first I would say we're certainly not going to wait until that has launched in order to start working on the next thing. We're going to have several things in the pipeline at that point. But no, I mean, that's really where the fun begins, because with a successful launch and operation of that Gravity Ring project, now we start to scale. We start to develop the other pieces of orbital assembly equipment that we're going to need in order to build large structures such as Voyager Station, which is still our flagship project, but will hopefully not be our only project that we will be building toward by the end of the decade. So larger versions of the P-Star that will be able to build trusses several meters on a side at various radii, so that we can create the circular structures that we're going to need for Voyager Station and other related structures. The capability to build these large habitation modules, which will be pressurized and be able to hold on the order of, as many as a couple of dozen or several dozen people at a time, as well as other key capabilities that will allow us to assemble these large complex structures in space. And so we're going to have a series of projects that will be ongoing and funded so that we can launch something every year or two up until we're able to start collaborating on Voyager Station.
So as the system becomes more developed, and we are aligning ourselves with future partners, if as an investor, at what point would the investor logically be able to anticipate some form of ROI?
We hope that it will start with the Gravity Ring. because while it is a technology demonstration project, we are also planning to have it host payloads that outside partners will be willing to pay for. And so while it's not a guarantee, it is our intention that we will have paying customers to fly on the gravity ring in every project thereafter. So the ROI could begin to accrue in a couple of years' time. There will be many other opportunities for generating revenue along the way as well, including pre-sale of Voyager Station habitation space. And that's definitely part of our development plan as well.
I might mention that we've been talking with people about potentially using the gravity ring for various kinds of experiments and demonstrations, and to have artificial gravity at levels somewhere between 0 and 1G, which essentially humanity has only had experience at those two levels. The 1 to 3 days on the moon are not enough to see anything about long-term effects of reduced gravity, and wasn't able to do many kinds of research that need to be done at reduced levels of gravity. These people are not just interested, they're champing at the bit to get some of this intermediate level gravity experience with such things as biological research, combustion research, a wide range of different things that can be done at intermediate values of gravity.
Yeah, I'll add actually that, NASA and the rest of the space community globally want to send people back to the moon as well as onto Mars. And these are both examples of reduced gravity environments where there's still a huge number of unknowns, both physical and biological. And we think that a platform such as the Gravity Ring, Voyager Station, or other rotating platforms that we might make to order for the right customer can help greatly advance the state of knowledge for all of these systems. And I think we could play a really key role in preparing humanity for operations on other gravitating bodies throughout the solar system.
I wanted to circle back to the D-Star. I don't think that it's been said yet, so I really did want to draw attention to the scale of the D-Star was 50% of what the anticipated size will be for the enclosure of Voyager Station. Can you speak on that a little bit, Tom?
Yes, indeed, the main, what we call the outer ring truss for Voyager Station, the cross section will be 4 meters by 4 meters for our current design. So that's double the linear dimensions of the D-Star, which was 2 meters by 2 meters inside dimension. We'll have an access tunnel that runs through that, connecting all of the different modules of the Voyager Station. And actually, the truss is most useful during the construction phase. It becomes a structural backbone during the construction phase, allowing things like modules to be attached and held in position while the rest of the station, other modules, spokes, and so on, are being installed. Once the station is spun up, it's more of an alignment tool than a structural backbone. It does help to keep things straight, but most of the stress is taken up by other members. But it's critical during that construction phase to keep things aligned and to make sure that the parts fit together properly, the parts being the modules and the couplings between modules, make sure that those fit together properly during the construction process. The D-Star demonstrated the joints between the parts of the truss. We have pieces that we call frames. There are longitudinal frames and transverse frames, and it's the joint between various frames, 2 longitudinal frames and a transverse frame, that are the main IP that we've developed and were the main demonstration that we did with the D-Star. That same kind of joint will be used for the ORT on Voyager Station, and we're just really happy. We're thrilled that the joint design works so well with the D-Star.
Yes, we are thrilled about that. So this mission that's happening in 2 years, and then a very aggressive timeline to a station scaled to the Voyager station in the next 7 to 10 years. That's really aggressive. Isn't the construction going to take a lot longer than what we're initially anticipating?
I don't think it'll be the construction that will take long. It will be getting the tools built, tested, and then launched in time to be able to put things together. These devices are actually designed to build these structures very quickly. As long as we can get the material up there, bolting them together and getting them in position actually takes on the order of days, maybe weeks at the most. It's not going to take years. I think a lot of it will be up to how quickly we can build those key pieces of machinery to do that, and then of course funding to be able to pay for all of it at the right time.
Yeah, I think when people look at space construction, they look at the example of ISS, which did take decades to design, engineer, launch, assemble. What we're doing with Voyager Station and our large structures is it's very repetitive, and so have the engineering, design, and fabrication of the tooling for one component that we then just duplicate multiple times. So there's 24 replical modules that the structure of them is identical. The truss itself is made up of hundreds of identical sections and members. So, and that's where Tim Clements, his expertise comes into play as well, because he's set up large manufacturing facilities in his career. And so it's like Jeff was saying, the tooling and the factory to build it is really the challenging part, and then we just keep knocking out components and go from one to one. Tim, did you want to add
Rolling
anything
on.
to that?
Looks like we lost Tim there for a minute, but yeah, you're back. Okay. Just to elaborate on that, the repetition and the accuracy, once we build these prototypes and these sections, a prototype within a prototype within a prototype is something similar that we're going to be doing for these items that are repetitious. And once we dial in the tolerances and the ability in the machinery to be able to reproduce the same item over and over again, we can very rapidly produce these parts in a manufacturing environment that we will control. So the engineering design will take longer than it will take to build it, in all honesty.
So, okay, so I understand obviously how this is all coming together, but doesn't this also mean that the launch costs and getting that much mass on orbit to put it together, isn't that somewhat prohibitive at this time?
Not necessarily. We are witnessing a real revolution in launch costs right now and over the last couple of years. There are several companies in existence who are not only commercially competitive, and so they're sort of driving a lot of the waste out of launch that has traditionally been paid for by governments with a lot of, I won't say extra money, but with a lot of money that is not necessarily earned as dearly as in the private sector. And these commercial launch companies are figuring out ways to provide launch at a fraction of the cost that it used to be, and mainly through the use of reusability. So, companies like SpaceX, I think, really paving the way, but also Blue Origin and others are thinking of some very creative ways, have already, to bring the launch costs down to a fraction of where they were, say, a decade ago. And we expect that this trend is going to really accelerate in coming years. And so, regardless of who winds up providing the launch vehicles for Voyager Station, or it could be a combination of different launch providers, we're confident that getting the mass up there is not going to be the most expensive component of this endeavor.
Yes, it turns out that
isn't it necessary for us to have multiple launches to just complete a single mission? I mean, how are we going to account for scaling all that mass? Tom, what were you going to say?
I was just going to say that it turns out that with the coming decrease in the access to space costs, not by a factor of 2 or a factor of 5, but orders of magnitude decrease in the cost of access to space. We'll be able to put, as Jeff said, we'll be able to put the mass in space for a relatively small fraction of the cost of the entire project. For 6 decades now, mass has been the driving concern for any kind of space activities. How much mass does it take to put up there to do whatever it is that you're wanting to do with your mission? And as long as mass is the driving concern, that drives you towards new technologies that will enable the capabilities you need to do your missions. But new technologies always bring with them risk, they bring development costs, and they also bring schedule uncertainties. And this is one of the reasons that we're going to existing technologies. Maybe we'll spend a little more sending that stuff into space, but at the reduced cost of access to space that we'll be seeing in the very near future. That cost will be relatively low, but it will buy down a lot of risk. It will buy down cost of technology developments, and it will buy down schedule uncertainties associated with technology developments. So we're very happy to be operating under this environment where we're anticipating orders of magnitude decrease in launch cost. It allows a lot of approaches that would not be possible otherwise.
Yeah, and to answer your question though, Rhonda, it will take multiple launches of a heavy lift vehicle in order to provide the skeleton of what we're going to need for Voyager Station. We can operate it before it is fully built out with just a fraction of its full complement of modules, but a large fraction of that will have to be constructed ahead of time, and that will require multiple launches. But with launch becoming more of a commodity at commodity prices, we're confident that that's going to be able to happen, and we won't be limited by the schedule of launch either.
So there have been a lot of criticisms. Our timeline is not realistic. Our objectives are not achievable. What are your comments on some of the feedback that questions our wherewithal to be able to do this successfully, and to also enable an industry that needs this leg up?
Well, you see this kind of criticism whenever somebody's going to do something that's really new. You see this kind of criticism, but sometimes it's justified, often it's not. 10 years ago, there were a lot of people that just laughed off SpaceX, saying that they were going to, and this was admittedly somewhat audacious, they were going to land Falcon boosters upright and reuse them. But about 5 years ago, those people that were laughing had to quit laughing. And now the people that had banked on SpaceX failing in that endeavor are feeling that in their wallets. Just because something is new and has never been tried before doesn't mean it's impractical. We have done our calculations, and we don't need any unobtainium or any other unavailable items. We're ready to go.
What about some of the other naysayers that are getting a bit more specific? They're saying that this is vaporware, or a campaign to sell swag. What would you say to them?
Well, as far as swag goes, it's a great way to support a company you believe in. We're not going to be able to build Voyager Station with swag for swag sales, but
I also think if you look,
if we could, that would be revolutionary.
I mean, yeah, it'd be a lot of T-shirts though. But go ahead, Tim.
And I was just going to say, I think if you just looked at the gentlemen on this call and the people in this team, you look at our backgrounds and the things that we've done, they're not things to just put in the past or they didn't happen. I mean, I could quite happily walk around any naysayer around to any structure that I've built around the world 10 times and say, you told me I couldn't build it, I'll show you. And I think we are all not here to waste time. We're here to move forward with technologies and leverage our networks and our experience and all of those things to move this forward, because we have a viable solution for the next level in space industry.
Case in point, the D-Star is not swag.
Or vaporware.
Or vaporware.
Right. Yeah, I was going to say, I think almost every company, has to start with a PowerPoint presentation to get people excited. But some of them stay in that stage for the next 10 years. We have already moved into the realm of hardware, and we plan to stay there going forward. So we mean what we say, and we're going to be building it and proving it to the world.
Tim,
and I think I'll just add that there's a healthy level of skepticism that's important for us, right? It keeps us motivated and driven and pushing ourselves. So I wouldn't discourage the haters. We'll show them through our actions, and it keeps us honest. So I appreciate it.
Yeah, fair enough. We all like a good challenge. We deal with them every day in our own work. So, we wouldn't be doing this if it was a piece of cake. It's obviously challenging, but
I think I see naysayers as an alternative way of thinking, which spurs me to solve another problem. So please keep it going.
And that's something that this team does not shirk away from. When we have challenges and problems thrown up against us, we take them on. We don't try to sidestep them or shirk away from them. We take them on and solve them.
Well, thank you. Thank you to all of you for your time this evening. I really do appreciate it. Do any of you have any parting thoughts that you would like to share about our objectives and our path forward for the next couple of years?
I was just going to say that this is, part of our motto, and what we talk about is space is for everyone. And this isn't an effort where we're just going to do this on our own. We appreciate collaboration with technologies that might be emerging, already developed, or in someone's head. We can still bring all those items together and help us move forward with our mission. So anyone who wants to, provide insight or be a naysayer or have skepticism, we welcome it. It's part of who we are and how we're going to move forward.
I will echo that comment about space being for everyone. One of the things we envision is that down the line, our techniques and the facilities that we build and the infrastructure that we build in the solar system make space not just available, but affordable for the average person, so that when somebody wants to take a vacation, one of the options is, do I want to go to space? For some people, it will be, do I want to live in space? And I see the development of OAC's vision and mission being providing the infrastructure that makes that possible.
Yeah, absolutely.
And I was going to say, we started this conversation with Jeff talking about a group of like-minded space enthusiasts got together and started talking about why hasn't this happened yet. And so I'm looking forward to being part of this and making it happen. And we're looking for people that share that same vision. And we have a lot of supporters and fans who are following us closely, and we're so grateful for them, our investors. And we're all going to do this together. It's not just a few of us. We see it as a global effort, an effort of humankind to take this next step.
I hope you enjoyed today's episode and visiting with part of the team of Orbital Assembly Corporation. Please email us if you have any questions about the team or the company. You can also sign up for their newsletter on their website at orbitalassembly.com, and you can also follow them on Facebook.